All right. What are we doing? Anyway, okay. So we're gonna start with rate of reaction, and we'll come to an experiment in a moment. Just start off with a quick definition. Can you define rate of reaction? Can you come up with units for rate of reaction? Units, I can't remember if we covered them in the last rate topic, but if we didn't, we'll cover them again now. But a definition of rate, a good way of thinking about a definition of rate is if you wanted to measure the speed of a car, what would you have to measure? Speed of anything. So assuming you're not sitting in the driver's seat staring at the speedo, you'd have to measure. What would you have to measure?
Distance and time. Distance
and time. Okay, so you've got to have those two things, haven't you? Distance divided by time. So you can't measure the distance of a reaction. What do we measure?
Measure reactant used or product produced.
Okay, so we can measure the change in the amount of reactant or product, either the amount of product produced or the amount of reactant used up. We're just going to time that up a little bit and say the change. Change in concentration. There are other ways of measuring rate, but this will actually make our lives a bit easier, so we don't have to worry about volumes of gas or anything else. Change in the concentration either of reactant or product, so product produced or reactant used up. And then don't forget the time bit, okay? So it's change over time. We're always going to have that time element. Units, so if we were measuring change in concentration over time, I'm going to go for some units there. I was looking at Matthew there.
So moles per dm cubed over seconds.
Okay, so per second, yeah. So moles per dm cubed per second. So per second is 1 over second is seconds to the minus 1, yeah. So as I said, by sticking with concentration as our change, we'll have the same units. So units of rate from now on, to keep things simple, will always be moles per dm cubed per second, and they're usually given to you in the exams, in the questions. Okay, so having said all of that, let's go back to GCSE, or not GCSE, back to required prac 3, when we did the disappearing cross experiment. So you remember this. So you get a flask containing some sodium thiosulfate and some HCl. React those together, and then we look down the flask through the solution, and what happens? What happens? Goes cloudy. Do you remember why?
Isn't it the sulfur precipitate?
Is perfect, yeah. So as well as some sodium chloride solution and a little bit of SO2 gas and some water, we end up with some solid sulfur which gets precipitated, so the solution goes more and more cloudy, and eventually you can't see the cross, so we stop the timer. Okay, so let's do a bunch of experiments. We're going to we might have, no, what did we do? Did we do temperature last time? I can't remember. Let's do concentration anyway. We're going to measure the concentration of sodium thiosulfate, and we're going to change that for a whole bunch of different experiments. And then, without worrying too much about what rate actually is for this experiment, let's say we've got a way of working out rate. Okay, and then we're going to draw a graph. So we've done 5 different experiments with 5 different concentrations of thiosulfate. For each one, we've measured the rate, and then we're going to draw a graph of those five rates. Could you plot that graph, or just draw a sketch of that graph in your book. Just literally one arrow, two arrows, and a line.
We presume there's excess HCl for
Well, the HCl is a control variable. It's going to be kept the same for all of them. That's the key thing there. Oh, very warm. We're going to get this weather on Friday. Sports day, that'd be nice. Cracking the flags. Draw us a line, please. Thanks. Okay, we've got some straight lines, some bent lines. Slightly more bent than straight, if I'm honest. Could you explain your graph, please?
Like if there's very low concentration of sodium thiosulfate, do you have enough concentration for it to start to react? So I started it off as 0 for a bit, and then it goes
0
up.
is fine.
And it goes up.
But your line's not straight. That's what I'm asking about. Why is your line not straight?
Not sure.
Okay. John, your line's not straight either. Why is yours not straight?
Well, I assume that if you keep increasing concentration, you're just going to keep increasing rate. I think at some point there'll be another factor limiting reaction.
Okay, so yeah, if we had silly concentrations of thiosols at 100 mole per dm cubed, then you can't keep increasing the rate. Okay.
Yeah, I was going to say, if you keep increasing the concentration of, we assume that there's enough HCl for whatever.
Yeah, that's what John's saying. So eventually, you will run out of HCl, but for fairly normal concentrations, 0.1, 0.2, 0.3, 0.4, 0.5, we would expect a straight line. But yeah, you're right, of course, if we kept on going, it wouldn't keep on going up forever. There would be a point where the rate gets limited by the amount of HCl. But that's fine, that's all we need for the moment. Okay, that's a particular relationship between those two quantities. What is that relationship? Jerry, have you got that one?
The concentration of sodium thiosulfate is directly
Directly
proportional.
proportional. What are the conditions for a directly proportional relationship in terms of a graph? Ask Finn that one.
The rate in which it increases is it increases by the same amount.
I'm asking how you spot it just by looking at a graph.
Linear line
Straight line
going through the origin.
has to go through the origin, that's right. So proportional is any line that goes up. Directly proportional is a straight line graph going through the origin, which you'd expect. If the concentration's 0, the rate would be 0, the reaction wouldn't happen. So that sounds reasonable. We should get a point down there. Okay. So that directly proportional relationship means that our graph will fit a mathematical equation. We know that the equation for a straight line graph is y equals mx plus c, but if it goes through the origin, then there's no plus c because c is the y-intercept and the y-intercept is 0. So in this case, y equals mx. Okay, so let's just lean on that a little bit. Y here is the rate, isn't it? X here is the concentration of sodium thiosulfate, and M, what's M?
The gradient.
Gradient, and that's constant obviously for a straight line graph, so I'm going to put in a constant, and the constant I'm going to use is a little k. I haven't just made that one up. That is called the rate constant. Okay. Now we already have a k, which is already a constant. What is our other k? It's a constant.
KC.
Okay, so we've got a big K. Big K is the, what constant is that? Okay, so big K is the equilibrium constant. We will be coming back to the equilibrium constant later. We've seen Kc, the equilibrium constant for concentration. So can we make sure from now on that your equilibrium constant is always obviously a big K and your rate constant is always obviously a little k, so we don't get those confused. We used to write in big capital letters and little letters as chemists because we use them in symbols all the time. So I try and deliberately put a little curl on my little k just to make it really clear that it's a little k. Okay. Right, let's do that experiment again. But this time, so this is kind of experiment 2 over here, and experiment 1. Experiment 1 was doing a whole bunch of different experiments, but changing the concentration of sodium thiosulfate. Now we're going to change the concentration of HCl. Okay. Now, we would expect that we get a very similar graph, and we probably would do. As we change the concentration of HCl, you'd expect the rate to go up, but I'm going to fix it a little bit. And in fact, it's already a bit fixed in the disappearing cross experiment you do. I don't know if you ever noticed the concentrations, but the concentration of thiosulfate we use is 0.15 mole per dm cubed, and the concentration of hydrochloric acid we use is 2 moles per dm cubed. Now, you do need a bit more hydrochloric acid than thiosulfate. They react in a 2-to-1 ratio, but we've got more than 10 times the amount. The reason for that is if you have a 10-fold or 5-fold, whatever it is, 7-fold excess of HCl, then making small changes to the concentration of HCl doesn't make that much difference to the rate. And that's deliberate because it means that if we measure out the HCl a bit wrongly, if we measure, I don't know, 9.5 mils instead of 10, probably won't affect the experiment very much. So let's do that experiment when we're changing the concentration of HCl, but it's having no effect on the rate because we're using such an excess of HCl. There's always plenty, however much we add. You know, if it's 2 molar and we make it 2.1 molar, we've already got more than we need. So what does that graph look like? Can you draw that one for me, please? That's the smallest graph I've ever seen there, Abraham. But that's good. You can get the details in there. That's good. Good. Like it. Like it.
That's it.
Okay. That's lovely. Okay. So technically, what you've done there is you would always get this, but I'm interested in this bit of the graph. Some mind changing there. That's great. Okay, so I'm aware that it's a bit of a fix, and I have tried doing this, by the way. So you start at 2 molar and you go up 2.1, 2.2, 2.3. And the graph you get does end up more or less like that. Goes up a little bit, so it makes a tiny difference. But if you have a good excess of HCl, so I'll just put that when HCl is in excess. Look them up, they were a rock band in the 80s. Okay, so what would be my equation for this graph here?
My equals x. So what rate equals the
Y equals x. No, y equals x.
Mm.
Would look like that.
y equals cons.
Y equals c. Yeah. So the concentration of the HCl isn't affecting the rate anymore. That's the point, right? We've taken the concentration of the HCl out of the equation, literally. It's no longer in the equation there. So if I was to write my rate equation for that, well, it would just be rate equals K. Would be there, wouldn't it? K. So I could do two sets of experiments. I could do my experiment for thiosulfate and do my experiment for HCl, and then I could take all of that data and stick it together. And I could say, okay, so rate is affected by the concentration of thiosulfate. It's not affected by concentration of HCl. So I'm going to do a little bit of maths, sleight of hand. So the thiosulfate is going to stay there. We want the thiosulfate to be in the equation. So I'm going to raise that to the power of 1, because anything raised to the power of 1 is just itself. HCl I'm going to raise to the power of 0, because anything to the power of 0 is 1. So that means that the HCl term sort of disappears from the rate equation. I've put it there, but it's not there. It's kind of there, but not there. But more importantly, it gives me a way of labeling these different types of effects. So I'm going to call this graph over here first order, because I'm raising the concentration of thiosulfate to the power of 1. And I'm going to call the HCl graph 0 order, because I'm raising the concentration of HCl to 0.
So, you know, so if like second order and third order,
There's no third order, but there is a second that we'll come to now.
would it be like, I don't know, defect is like it squares it, or it
Well, let's
I don't
have
know how to
a
explain it.
let's have a look at that. Okay, I will.
If you
cut
increase
this all
it
out.
by this much, the rate would increase by. Yeah, it's like an exponential.
Okay, so that should have been in orange, shouldn't it? Let's say I've got a reaction where A and B react to make C. I'll talk about why second order reactants appear later on, but for the moment just accept that they can exist. And let's say it's second order. We say second order with respect to, if you come across that in maths, with respect to WRT, the concentration of A. So here it was 0 order with respect to concentration of HCl. It was first order with respect to the concentration of thiosulfate. Now it's second order with respect to A, whatever A is. Could you draw that graph, please? So a second order graph with respect to concentration of A.
technique.
What conditions okay,
So it's
What's
like
the
conditions
right? I'll talk about the conditions when we understand a little bit more about rate and rate order and how they arise.
exponential.
So for the moment, just accept that this reactant is second order. So if I change the concentration of that reactant, how would that affect the rate? I'm interested in the graph.
Jerry. It's like exponential growth.
It's not
Oh,
exponential.
all your constants.
Thanks for playing.
Right.
That's not an exponential graph.
Ah. Is it right though, sir?
Yes, it is right. It's not exponential.
Exponential.
What kind of graph is it?
Quadratic.
Right, quadratic. That's better. Yeah. So here we're looking at rate
Look at half quadratic. Jerry.
is the concentration of A. What comes next?
Squared.
Squared, because that's what zero order was to the power of 0, first order is to the power of 1, so second order is to the power of 2. So second order, so we're looking at a quadratic graph. That again should start from the origin, but it goes up. Well, you've drawn plenty of y equals x squared graphs before, I'm sure, in maths. The difference is exponential graphs don't go through the origin. We will see an exponential graph later.
We're doing that in maths now.
People didn't used to know what exponential growth looked like until COVID, and now everyone is familiar with exponential, but we have to remind ourselves that it's not always exponential. Okay, all right, so let's put all this together then. First of all, let's just clarify what we mean by rate order. So rate order is the power that a concentration is raised to in the rate equation. That's the rate equation there. Okay, the rate equation is the rate equals k times ... So rate order is the power that a concentration is raised to. In the rate equation. So let's just no, we've already got C, D, and E. There we go. Let's say our reaction is first order with respect to A and zero order with respect to B and second order, could have done that as a number, order, I'm having trouble with that word today, with respect to C. Could you write me the rate equation, please? That's it. They're both correct. They will both be marked correct in this.
Yeah, it's not.
Right.
So,
Hello.
if with zero order with respect to B, do you
Yes.
even need to write B?
So they're both acceptable. So we can either write rate is K and then just go through them. A to the 1, B to the 0, C squared, or we could just say rate equals
That's it.
K, A, C squared. We don't need the number.
Yeah.
We don't need to raise A to the 1 because A to the 1 is just itself, and we don't need to put B in. Either of those is the correct rate equation for this reaction. Okay. One little note, and we will come to this later on, but you cannot determine rate order from just looking at an equation. You can't, I mean, I know it's just A's, B's and C's, so it's obviously just made up, but there's nothing about the equation which will give you that information. Remember when we worked out the equilibrium constant Kc, you just do it from the equation, didn't you? You products over reactants raised to the power of their balancing numbers and blah blah blah. You all know that. But for rate order, we actually have to do this stuff. We have to do an experiment and change the concentration and find out how rate changes when we change the concentration. You can't do it just from looking at an equation. You've got to get your hands dirty. And talking of that, here's a little challenge for us. Okay. So you've got 3 graphs now.
So the E's gone.
Yeah. Okay. So we've got rate, what did we say? Concentration of B was 0 order. Concentration of A was first order. Do it that way around. Concentration of C. This is just a summary. You've got all these graphs already. You don't need to draw them again. So we've got 0 first and second order, and our graph went across, directly proportional x squared. Okay. Just a summary. Don't need to write all of those again. But there's another experiment we can do that also produces a graph. So just hang fire here for a moment. I'll come back to those in a sec. Here's my flask with my reaction mixture, but this time I'm going to be making a gas. Maybe it's metal and acid. Here's my metal fizzing away, making a gas, hydrogen gas, and we're going to collect the gas in a gas syringe, which of course has numbers on the side, and then we're going to let's take a reading every
30 seconds.
I think we'll go 10 seconds, but thanks for sharing. Okay, and we're gonna go for the volume of gas, centimeters cubed. Okay, so you can imagine that. It's called continuous monitoring. Continuous monitoring is where we watch one experiment take place and we take readings every certain amount of time. Could be 30 seconds, could be a minute, whatever it is. We take a reading every now and then we draw a graph. But I just want to focus on the fact it's a different graph now. All of these are concentration versus rate, whereas now I would be recording volume of gas up there against time down there. Could you draw that graph for me, please? Let's say it's magnesium and acid here. How would that graph look? Again, just a sketch. It's just the shape I'm interested in.
So you make a theoretical like what you would actually get if you did it yourself.
Sorry, what was the first part?
Would you make a theoretical what you would actually get if you did it yourself?
Well, it's usually pretty similar. I mean, it's a standard GCSE prac, but we will have a go at it later on. I think it's on the continuous monitoring's on required prac 7, so we will get to that later in this topic. But it has a fairly standard kind of look and feel. So we're measuring the volume of gas appearing in the gas syringe. Is that it? Still starts at the origin, yeah? Because when I have 0 time, I'll have 0 volume of gas, yeah? So we're going to start at the origin. That's lovely. That's the wrong way around. That's lovely. That's definitely not right. Okay, so usually we get a graph like that. Why do we get a graph like that? We didn't do this wrong. Finn didn't do this graph. Why do we get a graph like that, Finn?
Probably gas range fills up and then you can't get any more, or the reaction ends before.
Okay. Reaction doesn't just kind of go for a bit and then end though, does it? That would give us a different shape. It has this very particular curve. If I was measuring the amount of reactants, we'd get a similar kind of curve for reactants as well. If you were in a physics lesson now, we'd call that a decay curve. It's a chemistry lesson.
That's less reactants.
But it's the same kind of curve. But why does it have that particular shape is my question. Can just let me think about it.
The rate of reaction changes based on the amount of products and reactants you have.
Yeah. But again, why that shape? What is that shape? What's going on here? What's happening here?
It's like a linear increase at that point.
What could you tell me about the reaction going on in the flask at this point? Compared with, say, this point?
It's reacting faster.
Right. So faster here, slower. What's stopped? Okay, so when it's level, when it's horizontal, which the reaction stopped. Okay, so fast, slow, stopped. What is represented as rate of reaction on this graph? The gradient. Okay, so you might have done this before. I don't know. It's a fairly standard GCSE activity, but if you wanted to measure the rate at the beginning, you draw a tangent to the graph at the origin. We will do this later. We'll reinforce it, and then you measure the gradient rise over run at that point, and that will tell you the what we call the initial rate. But the graph has a fairly sort of standard decay about it, in that it starts off fast, slows down and stops, because we're using something up. It depends what it is, but let's assume we've got plenty of magnesium. So at the start of the experiment, you've got high concentration of HCl. As the HCl gets used up, you've got lower concentration, so the rate of reaction is going slower because, the stuff, fewer particles per unit volume, and then at the end we run out of a reactant, so the reaction's stopped. Okay. However, so this is continuous monitoring now.
Yeah, on it.
That's only if it's a first order reaction.
Do you ever do that to differentiate the graph?
So would you get the marks if you differentiated it?
If you differentiation is not a part of A-level chemistry.
Maybe degree chemistry.
Yeah, it should be.
There's a lot of differentiation in degree level chemistry. Yeah, rate of change is it's a very standard first year task to analyse rate of change. But let's not worry about that. What do we got here? BAC. No, sorry, no. These are all time, of course. They're all continuous monitoring. Now, I said at the beginning of the lesson that rate of reaction is change of concentration of a reactant or product over time. So that's why I'm putting concentration on the axis here. But you can see why these two sets of graphs might get confused, because these have all got concentration on as well. These are concentration against rate, where I'm changing concentration as the independent variable in a series of experiments and finding out the rate of each. Whereas this is just one experiment. It's a continuous monitoring of an experiment where we're producing a gas or whatever it is, or the concentration's changing and I'm somehow able to monitor it, maybe by taking a sample every 10 minutes and doing a titration, whatever it is. That's what a first order continuous monitoring experiment would look like. What do the other two look like? I'm going to leave you with that for a minute. I'll just pause that. Most people have got the first one. Some have got it slightly different than others. Which is your first? Your zero order, sorry.
That one. That one.
Yeah, no, I prefer the line you rubbed out. What have you done to yours, Ewan?
Mine goes straight up, like directly proportional, but then goes straight and straight.
Why does it go straight?
Because
Or flat, rather?
flat because the reaction's finished.
Yeah, reaction's still going to end at some point. But remember we said for first order, the graph levels off because the concentration of a reactant, let's say the HCl, the concentration of HCl is going down, and as the concentration goes down, the rate goes down. It's first order. But here, the concentration doesn't affect rate because it's zero order. So the reaction is still proceeding, but the changing concentration of the reactants isn't affecting the rate. Until, of course, it runs out, and then you won't get any more product, will you? Because it's the reaction's finished. But up until that point, it'll proceed at the same rate. Okay. What about this one?
It's going to be more steep.
Well, isn't steepness a factor of the units or the numbers that you put on the time axis?
Increased gradient.
But yeah, but it's the order. It's squared, isn't it?
It is squared, yeah.
It's going to be. I don't know, it's just the effect of it. It's like I don't know how to explain it, but the effect on the gradient would be like it'd be like 3 to the power of 1 and then 3 to the power of 27, like you're squaring it's like steep. I don't think it would be difficult.
Yeah, but the steepness depends on. I mean, if I took that graph and I squeezed it so that it was on that kind of axis, wouldn't it look steeper? You know, instead of it being over that range, it was suddenly over that range. Wouldn't it look steeper? The steepness isn't reliable. It depends, and we could all draw the same graph from the same set of data, and you know he'd use more graph paper than you, and his graph would be shallower.
So you'd have a higher gradient.
Well, either you'd have to do some maths on it, you'd have to analyse the rate of change, or you wouldn't be able to tell the difference, which is what we're going to come to. Can't actually tell the difference between these two graphs. You can't tell if something's first or second order just based on a continuous monitoring experiment. You'd have to do this. You'd have to do a series of experiments at different concentrations and plot the bigger graph to look at how rate changes with concentration. These two are interchangeable. Zero order will stand out, but first and second won't. Okay.